All right, hello. My mic is on. It's 9:41, so let's get started. Welcome back to Data 100. Today we're going to be talking about feature engineering, which is what I wanted to cover on Monday but ran out of time to, and the bias-variance trade-off. So far we've talked about linear models. We talked about using a constant model, or using a simple linear model, or using a multivariable linear model. And although it seems rather limiting that we only use linear models, we've talked about linear models so far, it turns out that with linear models you can you can model some pretty complex relationships by using what's called feature engineering. There is a cost to doing feature engineering, and the cost of doing feature engineering is that sometimes you overfit your data, and we'll talk about what that is and how the bias-variance trade-off addresses this. So homework 5 is out, and it'll be due on Friday. Homework 6 will be out on Friday, and it'll be due on Tuesday. So keep an eye out for those deadlines. Okay. So I've gone over this MPG dataset at length with you guys so far. And one thing I pointed out was that if you're trying to predict MPG using horsepower, it turns out that this relationship looks pretty nonlinear, right? So it kind of curves downward, but the shape of that curve is not particularly linear. And you can try to fit a line to this data, but in reality, it might be better to use a nonlinear relationship. Okay, so it turns out that you can use a linear model to capture nonlinear relationships between data by using feature engineering. So for now, we're going to limit our discussion to predicting MPG from horsepower alone. And the insight that we'll have is that we'll add a new column to our design matrix X with horsepower squared. All right, so here I have the design matrix, which has bias and horsepower, and I've added one extra column for horsepower squared. Okay, so it seems like a simple transformation to do. If I asked you to do this in Pandas, you could probably do it for me in 10 seconds. But what it allows me to do is when I fit a linear model to this table, I'm going to fit a quadratic function to my data, right? Because the linear model is theta sub 0 plus theta sub 1 times x1 plus theta sub 2 times x2. But x1 is horsepower, and x2 is horsepower squared. And this right here is a quadratic in terms of horsepower. Okay. So it turns out that this model will still call a linear model. And the reason why we'll call it a linear model is because it's linear in the model weights. All right? So a linear model does not have to be linear in terms of the variables of interest, but it does have to be linear in terms of theta 1. So I won't be able to do something like theta 0 plus log of theta 1 times horsepower. But I will be able to do something like theta 0 plus theta 1 times horsepower squared. If I add a new column to this table with log of horsepower, then I would fit a log model. If I add a new column to this table with e to the power of the horsepower, then I'll be fitting an exponential model. Okay, so you can kind of see from adding new columns to our table, we can model some more complicated relationships without changing the actual model that we're using, right? So with this model here, with this table, I can still use gradient descent. I can even use the normal equations that I showed you a few days ago. So I'm fitting a linear model, but when I transform the data before fitting the linear model, I can fit more complicated relationships. Okay, let's see how it works. All right, here we go. So I have here the MPG dataset, and what I can do here is create a new data frame. Here's a horsepower column. Here's a horsepower squared column. Let's take that and square it. All right, and I'll add a bias column. Bias, and the bias column is 1. Okay. I can save this in a new table. Let's call that HP. Okay, and this is my design matrix X. And I'm going to create my sample, my training labels here, okay? And so we see here that the first car has 18 mpg, the second car has 15 mpg, so on and so forth. Okay, so this is pretty standard. And what I'll show you now is instead of using the normal equations, or instead of rolling my own gradient descent, I'm going to use the scikit-learn package to perform linear regression. Right, so I can import the linear regression the regression model from scikit-learn. To work with scikit-learn, I type in the model and I initialize it. If I write this, it'll initialize a model, but it won't fit it to any data. So if I shift tab here, I can pass in some arguments to configure that model. So I'm going to configure it by saying that normally linear regression automatically adds a bias column, but since I've added a bias column up here myself, I don't have to ask scikit-learn to fit the intercept for me. So I can write fit intercept equals false. So I can configure my model, and then to fit my model to some data, I can do .fit on my x and my y. Okay, so the first argument here is the design matrix. The second argument here are the sample true values. Okay, if I do that, I fit in my data, and it turns out that in practice, I will do this rather than writing my own gradient descent or rather than doing the normal equations, because scikit-learn underneath the hood does some pretty sophisticated things to fit larger data sets. Okay, so here's my model, and I can take my model and make some predictions. Model.predict on HP gives me the predictions for every point in my sample data. Let's call that pred. And what I can do is plot for you horsepower, mpg. So here are my original data points, and I can show for you my predictions, like that. Okay? So you can see here that I've used the linear regression model, but I fit a curve to my data. Okay. Any questions about this? Okay. And if I want to take a peek at the coefficients of my model, this is how you do it in scikit-learn. You ask for the intercept underscore, and then you ask for the coefficient underscore. Okay, so it's a little odd. These attributes only exist after you fit the model in scikit-learn. But after I fitted the model, I can ask for, well, I get an error. Let's see here. What happened here? Oh, I see. Let's do that. Okay. And I can see here that the intercept, so I fitted the model like y is equal to, let's see here, 57 minus 0.4 times horsepower plus 0.001 times horsepower squared. Because that's how I read this table. Okay. So if you want to fit polynomials to your data, we can add what we call polynomial features. If I had polynomial features of degree n, or degree 3, then usually what we do is we add every possible combination of columns that have that degree. Which means if I have 4 original columns and I want to make degree 2 features, then I would keep the first 4 columns of my table. I would do x1 squared, x2 squared, x3 squared, x4 squared, and then I would also add every possible pair of columns, right? So here's x1 times x2, x1 times x3, so on and so forth. And you can imagine that when I go to degree 3, then I'll have like x1 cubed, x2 cubed, but I'll also have every combination of columns that has degree 3. So I might have like x1 times x2 times x3. I might have like 1 squared plus 2, or 1 squared times 2, so on and so forth. Okay, so when you add polynomial features, you usually add a ton of columns, but that lets you model some pretty complicated things. Okay. There is a trick if you take a more advanced class called the kernel trick, which will allow you to essentially do this polynomial features, but without having to add tons of columns to your original data. We won't cover it in this class, but if you want to keep it in mind, if you learn it in a future class, you can think, oh, okay, this is like my way of coping with the number of columns in my original table. Okay, so this is like our first foray into feature engineering. We call it feature engineering because we usually call the columns of X our features, right? So if we're using horsepower and horsepower squared, we would say that we're fitting a model with 2 features, okay? And feature engineering is kind of like adding new columns or adding new features to our data. And those new features hopefully will give us some more informative data values to fit a model. Okay. I want to show you one more type of feature engineering. So we saw in the MPG dataset that we have a column called origin. Okay. The column of origin has strings. It has USA, Japan, and Europe. We notice also that the origin column is correlated with the MPG in some way. So we have here USA, Japan, and Europe, and here's a box plot of the MPGs for each country. And it turns out that USA cars are not as fuel efficient as the other 2 places cars. And so the idea is like, well, if we have some data and it's categorical data, but it's somehow still correlated with our miles per gallon, our variable of interest. And so the idea we have is to say, okay, well, maybe we can encode those categories as numbers in a smart way in order to actually in order to throw it into our linear regression model. Okay, so I want to ask you a question, which is, one idea you might have is to encode USA as 0, Japan as 1, and Europe as 2 in our data. But this will not work out. Talk with your neighbor for 2 minutes and try to figure out why. All right, so if I encode USA as 0, Japan as 1, and Europe as 2, you can think about what that will do for my linear model, right? So if I encode my origin column and I just replace the strings with numbers, what's going to happen is my model will fit a single weight for those numbers, right? So for the origin column, my model will get the number, let's say like 2. Okay, so that'll be my model weight. If my model weight is 2, then what my model is saying is that Europe cars are twice as efficient as Japanese cars, right? And Japanese cars are like 1 level more efficient than USA cars, which is not quite right. Right, so we don't want to encode this column as 0, 1, and 2 because the model does not have the MPG does not have a linear relationship with these categories. Right? So if I go from category to category, I shouldn't increase my MPG. What I should do instead is fit a single weight for each category. So we're going to do what we call a one-hot encoding, which is to say we'll take our original column origin and we'll split it up. Okay, we'll split it up into 3 columns. 1 column for USA, 1 column for Europe, 1 column for Japan. And what we'll do for those 3 columns is each of the 3 columns will have either 0 or 1. If the original value was USA, then the USA column will have the value 1, and all the other columns will have the value 0. If we have Japan, Japan will have the value, the Japan column will have the value 1, but all the other columns will have value 0. And we call this the one hot encoding because for every row, we have one hot value. Okay, so the one here is like what we call the hot value. The other values here are cold. So every row here has one hot value. Okay. So to give you some intuition about the one hot encoding, I'll ask you this question, which is, okay, so if I have these data and I have these columns here, when I one hot encode my origin column, what do you expect the largest model weight to be? Probably Japan, because Japan has the highest overall MPG. And then next, I expect the largest weight to be Europe, and the next largest weight I expect to be USA. And because I've split up my origin column into 3 separate columns, or the 3 new features, my model will fit one new model weight for every feature. Right? So it will be able to say, okay, USA contributes some amount of MPG, but that differs from Japan and that differs from Europe in a non-linear way. So the model can arbitrarily set weights for each of the 3 columns separately from each other, and that's what we'd like to do when we work with categories. Okay, so the idea here is that once you fit a model to a one hot encoded column, you can interpret the weight of that column as the quote-unquote contribution of that category. Right? So if Europe contributes more to the MPG than the USA, then we expect the weight for Europe to be larger than the weight for the USA. Okay. So there's a problem with the way that I've shown you this one hot encoding. The problem is that if we add a new column for every category, the column of X will be linearly dependent. Okay, and that's a problem. And the reason why that happens is because the one hot columns will always sum to 1, but our bias column is a column of all 1s. All right, so let me show you what I mean here. If I have this as my X matrix, my training matrix, and I one hot encode the origin column, and I have a bias column here, all right? Notice how the USA column plus the Europe column plus the Japan column will always equal to the bias column. Okay, and that's the definition of linearly dependent, all right? And the problem with having columns be linearly dependent is that you won't be able to actually solve your normal equations. The reason why is because this matrix right here will not be invertible. Okay, so if you remember from linear algebra, you can only invert a matrix when all the columns are linearly independent from each other. And so this particular matrix, X transpose X here, will have linearly dependent columns intuitively because the original matrix X had linearly dependent columns. Okay, so if you put in linearly dependent columns into a recipe of matrix equations, you get out a linearly dependent column as well. Okay, so this is a problem for normal equations, but I mentioned before that we don't actually care so much about the normal equations for this class. Okay, so if you actually take the matrix on the left and use gradient descent will pretty happily just find for you some model weights that will minimize the error. But the problem is that even though you can do that and it won't give you an error, you'll have some problems when you interpret the model weights. Okay? So if you have linearly dependent columns, you can think of linearly dependent columns as being able to quote unquote swap model weights. And what I mean by that is this. Okay. So I have here my matrix on the left, and let's suppose, for instance, that my model finds that each of the 3 columns should have weight 3. Okay, so my model just says, okay, I'm going to do 0 times the bias plus 3 times the USA column plus 3 times the Europe column plus 3 times the Japan column. Okay, so far so good. I'm just adding some weights for each column. But it turns out that because the bias is a combination of the origin columns, if I set the model weights to 3 for the column bias and 0 for the rest of the categories, this will still give me the exact same prediction. Right, so this matrix here on the left, if I do 0 times 1 plus 3 times 1 plus 3 times 0 plus 3 times 0, this will give me 3, which is the same as this first row here, because the model weight for bias is also 3. And you can show that the prediction for the model will be the same. Okay, so between the left matrix and the right matrix, the predictions will be the same. And because the predictions will be the same, when I take gradient descent will give me either one, or a combination of the two, or something in between. Okay, and that affects my model interpretation because on the matrix on the left, I can interpret my model weights as saying all the categories contribute equally to the miles per gallon of a car. But on the model on the right, since I have 0 for each of the model weights for the origin column, I would probably conclude that none of my categories matter at all. Okay, so that's not so good, right? Because that'll affect the way you interpret your model weights. And that arises because you have linearly dependent columns. Yeah, Julie?
Sorry, can you just clarify what the bias column is for?
So the question was, can I clarify what the bias column is for? So we usually add a bias column to our original data so that we can fit an intercept term. So in a linear model, we have theta 0, which is not multiplied by any of the original x values. And so to cope with that, we add a column of all ones, and we call that the bias column. Okay. Any questions about this? Okay, so the solution here is not so hard. What we'll do is we'll just drop the last one hot column. Okay, so instead of having 3 columns for USA, Europe, and Japan, I'll just pick one of them and drop it. When I drop that column and keep the bias column, then my columns will still be linearly independent from each other, hopefully. Okay. Once I drop that last column, so let's say I drop the Japan column. When I drop the Japan column, gradient descent will no longer have the problem of having linearly dependent columns, which means that usually the model weights will be unique. So if I run gradient descent multiple times, I'll get the same model weights for the bias column, the USA column, and the Europe column. Okay, and so if I have the model weights, after I've dropped one column from one hot encoding, I can interpret the model weights for the USA and Europe as quote-unquote encoding the difference between USA and Japan, or encoding the difference between Europe and Japan. And what that means is that when I drop the Japan column, my model weights will try to fiddle with the bias until my line goes through most of my data points. But if USA cars are less efficient than Japanese cars, then the model will put a negative weight for USA. And if European cars are more efficient than Japanese cars, my model will put a positive weight for Europe. So you can interpret those model weights, and the interpretation is that the weights are kind of like the difference between this column and whatever column I dropped. Okay. So in Pandas, it's not super hard to do this. Here's the origin box plot again. And to actually do this one-hot encoding, what I can do here is make a new data frame. Here's a bias column. And you should know how to do this, which is you take the column, you check if it's equal to USA, you make it an integer, you do the same for Europe. And I broke something. Oh, I forgot to add a column. Oops. I do have to add a cell here. Here's the origins. Origins equals mpg.look. Let's just grab the origin column, like so. If I want to show different values in this origin column, I could do .look. So let's slice out a little bit of it. 0, 410. Okay, so now I'm just showing you some variety of values in this origin column. And to one-hot encode, I can just compare each value with USA and Europe. Here I have the bias column, and I don't have a Japan column. Okay, so if I take this data frame and go back up here to my scikit-learn and throw this data frame in the model.fit, gradient descent or scikit-learn will figure out what model weights work best for this design matrix. Okay. So there are two types of feature engineering that I really want you to know. Okay, so I want you to know polynomial features, and I want you to know one-hot encoding. Of course, there are many other types of feature engineering. So I'm just going to give you like a quick list of a few of them. But in reality, feature engineering is often domain specific. So what you'll do is you'll look at your data and you'll think about your problem, and then you'll realize that, okay, I should add these features because this fits my domain of interest. So one type of feature engineering is to standardize a column. You can log transform a column instead of taking the polynomial. You can do an absolute difference of a column from a set constant. So you can say something like, how different is the current temperature from 70 degrees? I can bin the data and then one-hot encode it, which you can interpret as saying, for example, are we driving during morning rush hour or evening rush hour or sometime in between? There's date-related features. There's image-related features. In general, there's a lot of types of features you can do. And a lot of using models effectively is trying to determine some smart way of encoding features that capture important information about your data. But they all share the same kind of common attribute of like essentially adding more columns to your design matrix. Okay, so you add more columns in the hopes that it'll give you a better fit to your data. All right, let's take a break. Okay, let's bring it back. Let's talk now about the bias-variance trade-off. This trade-off is like super fundamental to pretty much all of machine learning and like modeling. And in particular, the question is, okay, well, if I have many different choices of models, and I have many different choices of features to add to these data before we fit the model to them, how do you know when to stop adding features? For example, I just showed you how to fit a degree 2 polynomial, but you could easily imagine me fitting a degree 10 polynomial, a degree 100 polynomial. And it turns out that as I add more features to my data, my training error will generally decrease. The reason why my training error will generally decrease is you can imagine if I have a degree 2 polynomial, right? That's going to be like something times a times x squared plus b times x plus 1. If I add a new term for x cubed, if adding the x cubed would increase my training error, my model would probably determine that it's best to set that coefficient for x cubed to 0. Right? So if we add a new feature and it's useless or doesn't do anything for me, you can imagine that gradient descent should hopefully figure that out and decide that the model weight for that column is 0, which essentially means that my new model will be the same as my old model if that column is useless. Okay. And so what happens because of this is you'll notice that as I add more degrees to the polynomial, my training error will decrease. So my model will appear better than before. I'll show you what that means. Okay. So here I have some data on ice cream. And for ice cream, what these people did is they had people measure the sweetness of the ice cream and then had some taste testers measure how good they thought their ice cream was overall. So you can imagine that if you have ice cream that's really not sweet at all, it probably doesn't taste too good. But past a certain level of sweetness, and people like hate the ice cream because it's way too sweet. Okay? I would probably prefer ice creams like on the left end of this graph. If you haven't been to Humphrey Soclome, which opened on college, it's pretty good. Check it out. Try out the Vietnamese iced coffee ice cream. It's not too sweet. I approve. Okay. So here's my ice cream data frame. And I'm going to pull out the sweetness into my design matrix X. Here it is. Pull out the overall rating into my true values Y. Okay, so this is standard procedure. Okay. And what I can do now is instead of implementing for you the polynomial features myself, I can rely once again on scikit-learn. Okay, so a common theme in this class is I'll show you how to do something manually, and when it comes down to using it in practice, you'll probably just use scikit-learn. Okay, but it's important to know how to do it, because sometimes scikit-learn doesn't give you exactly what you want. For example, I'm fairly certain that the scikit-learn one-hot encoding will give you the one-hot encoding for all the columns, and so you'll probably have to drop one of them yourself if you want to do that model weight interpretation. Okay, so let's import the polynomial features. There they are. And the nice thing about scikit-learn is that all the transformers and classifiers work pretty much the same way. So usually what I'll do is I'll initialize my features and I'll say let's do degree 2. And here is my X data frame. And I can do features.fit on X and then .transform X, which means that it'll take my original data frame, add a bias column, and also add a squared column here for degree 2 polynomial features. Okay, so pretty nifty. I'm going to call this my poly matrix. There it is. And as before, I can fit a linear model to this. So here's linear regression. Fit intercept equals false. And I'm going to fit my model on this poly matrix and my true values y. And so here I fit a degree 2 polynomial to my original data. Okay. Again, I can plot for you, let's scatter plot, the sweetness against the overall rating using my ice cream data. And I'm going to plot for you on top of the original data here's my original data. I'll plot for you the sweetnesses along with my model's predictions. There we go. Okay, so similar to what I did before, degree 2 polynomial. Okay. I want to show you now a nice feature of scikit-learn that I personally use all the time, which is called the pipeline. And what you'll find is that when it comes down to fitting models in practice, you'll oftentimes do something like I did just now, where we'll do some feature engineering, and then after we do some feature engineering, we'll fit a model. And the problem is, like, this is a lot of steps, and I have to make a new variable for this feature engineered matrix. And so oftentimes what I'll do is I'll compose my feature engineering and model fitting into a single scikit-learn pipeline. Okay, so I'll show you what that looks like. Pipeline, import pipeline. Okay, and the idea is a pipeline in scikit-learn is a series of steps to fit a model. Okay, so here I'll first start by adding some polynomial features with degree 2. And then as my second step, I'll fit the linear regression. Like so. Okay, and I'll call this my model. Now when I use this model, what it does is it'll take in some input data, it will transform it, and then perform linear regression on it all in one go, which means that I can take my original X matrix, which is way up here, here's my X, and just do fit on X and Y. Okay, so I did not have to do the polynomial features myself, but if I include a polynomial features step in my pipeline, this will work as it did before. This output here is a little longer because it has all the steps, but you can see here that I managed to fit my data and I did not have to use, I didn't have to create a new variable for the polynomial features and fit it separately. Okay, so this is very convenient. And so what I can do is I'll define some functions. Here is the MSE function, the mean squared error. Here's the MSE of a model on my original overall rating for ice cream. Okay, so I have some more functions here. I have a function here that fits a polynomial model, but lets me pass in the degree I want to before fitting it. And what I want to show you is I'm going to increase the polynomial degree and fit the model over and over and show you what happens to my model. Okay? So here are my models. I'm going to do, for every degree, I'm going to fit a model with that degree, x and y, y, for degree n. And let's go from degree 1 to degree 10 polynomials. So this fits 10 different models in one go. And I can draw for you a few of those models. Okay, so the blue dots are my original points. Here is degree 1 polynomial, which is a line, right? Because degree 1 polynomial doesn't add squared. So here's the line. Here's the degree 2 polynomial. Here's the degree 5 polynomial. Here's the degree 10 polynomial. I could just keep going, right? I can increase that degree as far as I want to go. Okay, now I also want you to look at what happens to my mean squared error. Okay, so for a line, the mean squared error is 0.32. For a degree 2 polynomial, the mean squared error is 0.03. For a degree 5, the mean squared error is 0.02, so it's going down. And for degree 10, there is no error at all. And there's no error at all because this polynomial goes straight through every single one of my training points. Okay, so it just nails each one on the dot. But you look at this degree 10 polynomial and you feel a little uncomfortable, right? It just feels kind of wrong to do this. But the problem is, in real life, you will not be able to tell whether it's squiggly like this or not because you're going to have a bunch of columns in your data, right? So if you have 100 columns in your original design matrix X, which is not that uncommon, you won't be able to make this nice 2D plot here and try to examine these polynomials. And more fundamentally, right, sometimes this polynomial might be the one that you want to use, right? It could be the case that you do have some very complicated behavior in your population, and you actually do want a degree 10 polynomial. Okay, so what we're looking for is some kind of principled way to pick the features that we want to include in our model. And the problem here is that I cannot just use the training error to pick my model, right? Because if I use the mean squared error on the training data to pick a model, I will always pick the most complicated one. Okay. I can also plot for you this curve right here, which says here's my training error, and here is each like kind of point on this line here is a different model, and I'm showing you here that as I increase the number of features in my model, the degree of the polynomial, my training error just decreases. Okay. This right here makes us feel uncomfortable because it doesn't seem to be fitting like the overall trend in the data. It instead seems to be fitting like kind of like the minor fluctuations in our data points. Right? So if you look at these data points, your human eye says to you, this data point seems kind of like a quadratic with some minor deviations. And this model says, actually, I think all those deviations are very important. I'm going to make sure that I get every single little deviation away from the original model. Okay, and so when this happens, we call this overfitting. We're fitting the noise in our data instead of the actual underlying pattern. And oftentimes when we collect data, there is some noise. And the challenge here is to decide on the model that can fit the underlying pattern even in the presence of noise. Okay. So in general, adding features causes what we call overfitting. And the approach that we saw from data 8 is to say, okay, if we can't depend on the training error, then what we'll do is we'll split up our data into a training set, a validation set, and a test set. And the procedure in data 8 was to fit all the models on our training set, use our validation set to pick the model with the lowest validation error, and then use the test set error as our final reported accuracy of the model. Okay, we'll talk about why we do this after we talk about the bias-variance trade-off. In data 8, it was kind of given to you in like a hand-wavy intuitive way. The hand-wavy intuitive way of explaining why we do this is you can imagine yourself studying for an exam, right? And if you study for an exam, one thing you might do is look at some past exams. But if you look at past exams, let's say you like take 5 practice exams, okay? And you do all the practice exams, and you want to figure out how well you're going to do on the actual midterm when it comes around. Okay? Now, the training error here kind of refers to how well you did on the practice exams. Okay, so if you did, like, you took 5 practice exams and you record your scores for each of the 5, and you can kind of like feel intuitively that it's not so good to say, oh, I did well on my 5 practice exams, I should be good to go for the midterm. What you want to do is you want to test yourself on some problems that you haven't seen before. Okay, so what you might do there is you'll say, okay, I'll take a 6th exam and I'll just record my score for that, and I won't cheat by like looking at the answer key or whatever and then finish the score there. And I think that that'll be a more accurate representation of my score on the real exam. And the intuitive idea here is that if you pick your model based on how well it did on the training error, you're not going to get an accurate result because the model kind of cheated. Right? The model saw the data before, and now you're trying to use that same data to judge how good the model is. Okay, so that's the hand-wavy explanation, and I'll give you a more sophisticated explanation today. Tomorrow, we're going to upgrade this technique to what we call cross-validation, which is kind of like this, but a little bit more sophisticated. Okay, so I will go through the pieces I'll go through some pieces of estimation that I talked about last week, okay, and I'll apply them to models. If you remember from last week, we talked about estimator bias. Okay, so estimator bias says, on average, will I get the actual population parameter? Okay, for a model bias refers to, on average, will my model get the population model? So very similar idea. Instead of applying it to a single number, we're applying it to a model. So it's a little more sophisticated, but the intuitive feeling should be the same. Okay, so the idea here is that if my model is unbiased, then it has the capability of fitting my population model on average. So for example, if my population model was indeed a quadratic function, then fitting a line to the data is biased because it will not be able to recover this pattern. Fitting a quadratic is obviously unbiased. But fitting a degree 5 or a degree 10 polynomial are also unbiased because I can fit a quadratic with a degree 10 polynomial, right? I just set some coefficients to equal to 0. And so because of that, this has what we call, it has like the capability of fitting the original population model. And you can imagine that if I just had like tons and tons and tons of data, that this model here would kind of even itself out and realize that the quadratic model is the best in the end. Okay, so by unbiased, I mean that the model on average with like infinite amounts of data will be able to get back the population model. And so what we see here is that the line is biased because even with infinite amounts of data, it still will not be able to fit this curve, whereas these three models will be able to. They have the ability to. Okay, so that's model bias. And we also talked about estimator variance, and now I can talk to you about model variance. Okay, so what we say is a model has high variance if it has very different fits for the same data. Okay, so what I mean by that is we have these points, and the points are drawn from the population at random. All right, and when we draw points from the population, they're going to come back to us, but they'll be a little bit different each time we take a new sample. You can imagine with me that if I draw new points and I fit a line, the line will not vary too much. Right? It might jiggle a little bit up and it might jiggle a little bit down, but in the end the line shouldn't vary too much. And you can imagine also, so another way of looking at it is if I bootstrap the points, how will my predictions change? So if I bootstrap these points and fit a new line, I'm going to get a similar looking line. On the other hand, if I go all the way over to the right-hand side, and I bootstrap the points here, or I get new points from my population, I'm going to fit a pretty different looking curve, right? So like, for example, this hump right here might not be a hump, it might be a valley. This valley here might turn into a hump. Who knows what's going to happen to our model after we get new points from the population? And so what we say here is that, so that the visual change reflects the model weights changing a lot. So if I take new points from the population and fit models for each of those samples, my model weights will vary quite a bit, and that is like kind of a numeric capture of what we call the model variance. Okay, so we have these two axes by which we want to pick a model, and if you remember, we said before that for an estimator, right, we want the estimator that has the lowest bias and the lowest variance. And the way that we pick an estimator with the lowest bias and the lowest variance is through the risk. And the same way, we can do what's called the model risk. Okay, so the model risk, just like the estimator risk, kind of combines the bias and the variance in an intelligent way. Okay, here it is. The model risk is the expected loss over all possible points in the population. If you actually go through this algebra, you'll see that the algebra expands to this. Okay, and in previous classes, they would have like pages and pages of algebra to show you how to do this, but I decided not to do that for this summer. Instead, if you want the actual full derivation, I believe I put it in the textbook. Okay, but I do want to point out this final equality here, because this final equality shows us the model bias in the first term, the model variance in the second term, and what we call the irreducible error in the third term. Okay? So if you look at this expected value of f, right, so f here is our model, or our choice of model. Let's say it's a linear model. And the f star is the population model. So for the ice cream example, the population model could be a quadratic, and we might be fitting a line to the population model. Okay. The model bias says, how far off on average will my model be from the population? The model variance says, given some different data sets, how much will my model change? Okay. And the irreducible error here kind of captures the fact that when we sample data from the population, we usually will not get perfect values every time. Our points will vary a little bit. And there's nothing we can really do to change that. That's what we call the irreducible error. So no matter how we pick a model or how we do some feature engineering, we really can't get rid of this error here. But we can adjust the model bias and the model variance. In particular, we say that simple models have high bias and low variance. Complicated models have low bias and high variance. I almost said variance. Oh my gosh. Okay. So to give you a visual idea for what this is showing here, I'm going to say I have this. So on my left, I have the blue line is the population. Okay, and these green lines here are linear models that I fit to some different samples. Okay, so for my population, I took a bunch of samples, and for every sample, I fit a linear model. So I get these green lines. Okay, now the bias of my models, you can imagine as the average of these green lines. So the average green line, I plotted as this red line, and the bias here is, roughly speaking, how much this red line deviates from the blue line. So on average, my line will not capture the pattern, but it gets some part of the pattern. Right? It gets a little bit of it. The variance of my model is how much the green lines deviate from the red line. So my red line is my average, and my green line are models that I fitted on different samples, and the variance of my model is kind of like the spread of those green lines around the red line. Okay, and here's my irreducible error here. The irreducible error I put kind of small because it's not something I'm going to focus on too much, but intuitively it's kind of like the population model is a blue curve, but in reality I'm going to get points that are a little bit scattered around that blue curve. Okay, now contrast this with a more complicated model. Okay, so the same blue curve, although it's kind of hard to see here, the blue curve is in there somewhere, I promise. And what I've done is I fit degree 10 polynomials. Okay, and I plotted them all as these little green curves. All right, so we can see that the average green curve fits my population pretty well. It gets like almost all of the variance, or almost all of like the model's patterns. Okay. But the variance of the degree 10 polynomial is very high, right? So if you look at like how these lines deviate from the middle here and how these lines deviate, like this is like a hairball right here. And the variance, so we say the variance of this model is much higher than the variance of the line. Okay, and the idea here is that risk, right? Risk is a combination of bias and variance. Okay, so we're not too sure which model will actually do better in practice, because the risk is a combination of bias and variance. This complicated model had a low bias but a high variance. The simple model had a high bias but a low variance. But it turns out that we can determine some factors that influence the bias and variance. In particular, if our population model is linear and we use a linear model, then the bias of that model will be 0. Okay, so we'll get that population model on average, and the variance of that model will be what we call sigma squared times p over n, where sigma squared is the variance of our irreducible error, p is the number of features in our training data, and n is the number of points in our training data. Okay, so this is a very simple case, and if you go through the algebra, it requires like relatively sophisticated linear algebra to do, but this is one example where you can derive it, although I won't make you derive it. There are similar types of breakdowns for other types of models. I'm just showing you one that's common and one that we commonly use in this class. Okay, so how do you interpret this? You interpret this by saying, if the real model in the population is linear, then if you pick a line, we're doing a good job in terms of bias. And if you want to minimize the variance, then what we should do is make p as small as possible and make n as big as possible. So if I decrease p, my variance will go down. If I increase n, my variance will also go down. And the idea here is that to decrease the variance, I can remove features or I can collect more data. And this is generally true of most models, but other models have like special types of parameters that you can tune. For example, in data 8, we talked about the k nearest neighbor algorithm. And if you do the bias variance breakdown for k nearest neighbors, you'll get a term here with k. And in general, the variance increases as k decreases. Okay. So I mentioned before that the bias variance trade-off is a trade-off. And the reason why it's a trade-off is because you usually can only trade off bias for variance or variance for bias. So if you remove features, generally speaking, you can't capture as complicated of a pattern, which means that your bias will increase. Okay. Collecting more data is like a special case. Collecting more data is just good overall. But in general, when you pick a more complicated model or you make your model more sophisticated by using feature engineering, you'll increase bias or increase variance at the cost of the other. Okay, so now we can take a look back at some of the polynomial models that we're looking at, and we can analyze them in terms of bias and variance. Okay, so a model underfits the data if it has too much bias, and a model overfits the data if it has too much variance. Underfitting is caused by the model not being able to capture the pattern, and that means that our bias is high. Overfitting is caused by the model capturing too much of the noise, the irreducible noise, and that results from the fact that it has so much variance that it can vary so that it can wiggle these it can wiggle these curves so that it captures all the noise in my data. Okay, now the training error only reflects the bias. Okay, so if I use some data to fit my model and I look at the error of my model on the training data, that error only reflects the bias. If you remember, I showed you how the training error decreases as I get more polynomial features. And the reason why it decreases here is because the training error only captures the bias of my model. It does not capture the variance. Okay, the test error, on the other hand, captures both the bias and the variance. And so you can see here from this curve that, generally speaking, if I increase the complexity of my model, the bias will go down and the variance will go up, and the test error will be the combination of bias and the variance. So it will usually go down and then go up. And the best model that I want to pick in the end is a model with the lowest test error, not the lowest bias. Okay, and so this explains why we can't see that the model is overfitting our data from the training error alone. All right, some more features or some more trade-offs. So adding a good feature to our data usually decreases the bias because we can capture some more complicated patterns. But adding any feature, regardless of whether it's good or bad, will increase our variance. Because if you add a new feature, the model will have a new model weight, and that new model weight has some variability in what the model weight can be, and that means that our model will have more variance. So in general, you want to pick features that will decrease your bias more so than they increase your variance. Okay. The noise in a test set only affects the irreducible error. The noise in that training set only affects the bias of my model and the variance of my model. Intuitively, this is because the bias and the variance depend on the model fit. And so if I have noise or error in my training set, my model's bias and variance will be altered. But the noise in the test set is only reflecting the irreducible error. I'm not using the test set to pick a model. Okay. In general, if you want to fit a complicated model to some data, you need a lot of data. And the reason for that is because the variance goes down as you increase more data points, but the variance generally increases quite a bit if you pick a more complicated model. Okay, so you saw before how the variance increases with p, the number of features in my data, but you may also remember that when I use a polynomial feature of degree like n, I create a ton of new columns. And because I create a ton of new columns, the variance of polynomial features, the polynomial regression, increases quite a bit with the number of degree polynomial. Okay, so basically, if you want to fit complicated stuff, you need lots of data. And the reason why you need lots of data is because even if you pick a model with no bias, the variance of the model might be high enough that you need some data to balance out that variance. For example, we won't talk about neural networks specifically in this class, but in general, those types of models have low bias because they're very complicated, but they have very high variance, which is why Google throws like terabytes of data at these neural networks to fit them. Okay. I want to show you what this looks like. I have some data on, I believe this is on clothes. And what these researchers did is they took some clothes and they measured like the air volume of these clothes, and they're trying to figure out how resistant to evaporation these clothes are when they get wet. And I think the idea here is that like if a clothes is evaporative resistant, then maybe it'll be more comfortable, or like good for cold weather or something like that. Okay, so anyway, we have some clothes. And what I'm going to do here is show you the training error and the test error for several different models. Okay, so model selection, import train test split. And what train test split will do is it will split up my data. So here I have train test split. I will pass in, I'm interested in predicting the, let's see here, the air volume. I'm interested in predicting, the evaporative resistance from my air volume. So evaporative resistance, air volume, and I want my test set size to be 0.3. So here I have X train, Y train, Y valid. Okay, so I'm going to call this my validations. I'm going to call my second data set my validation set because I'm going to use it to pick a model, so to speak. So I have here X train, X valid, Y train, Y valid. I've taken my data set and I've split it up into subsets of my original data. So my original data had 39 rows. My new data set has 27 rows for training data, and the remaining rows go into the test data, or the validation data. Okay. Here we go. So I want to try out polynomials from degree 1 to degree 19. Here are my models. So poly model, and I'm going to train them for every degree in my degrees array. Here are my training errors. My training errors are the MSE of my model's predictions, predict X train against the training data, or model in models. Here we go. And then my validation errors are just the same MSE, but instead of predicting the training data, I'm predicting the validation error. There we go. And that's it. So I fitted 20 different models, or 19 models. Let's go to 20. Okay. So I fitted 20 different models to my data with 4 lines of code, which is not bad for Python. And I can show you the degrees on the x-axis and the training errors on the y-axis. We can see here that, that doesn't quite look right. Did I mess something up here? I might have switched these two around. Let's try this and see if I get something better. Darn, I didn't get something better. Okay, I might have messed something up, but in the interest of time, what we should have seen is that these errors go down with the degree polynomial. I'm not sure where I screwed up, but I don't want to like comb through my code to look for a typo. I do apologize. Let's take a look at the validation errors and see if those are also screwed up. So those just go way high. Okay. Let's see. Do I have my actual original code here? I do. Excellent. All right. This is what it should look like. Okay. So here the training errors should go down, And then what you might see is that if you increase the degree, it'll go up a little bit. But if you keep increasing that degree, my training error will go back down. My validation error, generally speaking, goes down and then back up. But in this case, it just goes up because my data were not super complicated to begin with. Okay. So in this case, I'll probably just get from this plot that I should pick the line, the one with degree 1 features, and I should just forego using polynomial features on this data because I only have like 30 data points, and the pattern looks relatively simple. All right, so feature engineering gives you some complicated models, but you should be careful with complicated models because of the bias variance trade-off. Looks like we're done for today, so I'll see you tomorrow.